be talking about solutions today. A couple things about glassware for our lab tomorrow. We're doing this lab work. I think you guys know, if you look up here at accurate glassware, a couple things missing. A regular flask, an early modern flask is missing, and so is a beaker, right? Those are not accurate pieces of glassware. Those are for holding liquids. Thanks. So please notice that, graduated cylinder is kind of like, if you have to, but there's better pieces of glassware. Burettes are very precise, and so are these pipettes. And so this is actually a volumetric pipette. See this word? That's a volumetric pipette, and there's like one little mark right here. And this one little volumetric pipette might be exactly 25 milliliters. And it's not 25 milliliters, it'll actually say 25.00 milliliters. And so like there's one line on this pipette, and if you get your liquid so that the meniscus is at the bottom of that, or the bottom of the meniscus is at that line, like you'll have 25.00 milliliters of liquid, which is really cool. But the thing about those volumetric pipettes is like you cannot measure 24 milliliters, you can't measure 1 milliliter. You can only measure that one thing. We actually have these, and we have them actually in 1 milliliter, we have 5 milliliter, 10 milliliter, and 25 milliliter. We have a lot of them. And you put a little bulb on them and you like scroll the bulb up, and I'll show you how to do that tomorrow. When we're making this solution, this is what we're going to be making them in. They're called volumetric flasks. And so what you do is, you know how I just told you, like, okay, you need to make 500 milliliters of this or 100 milliliters of that. Well, so if I told you to make 100 milliliters of a 3 molar hydrochloric acid solution, like you would go find one of these that's 100 milliliters. And there's also one single line on this, one single line, and you're gonna put your salt and your water in there, and then when the meniscus, the bottom of the meniscus is at the line, then you know you have not 100, but you have 100.00 milliliters, which is really cool, but there's only one line on them. So these volumetric pieces of glassware, they're very precise, and they only are for really one volume. And like I said, I'll show you that tomorrow. So, again, with the meniscus, make sure you're always measuring at the bottom of the meniscus. Also, I see a lot of people do this because it's easier to pick up, like if you have like you would not measure with this, but like people will pick it up and be like, okay, is that right? Are you really holding it flat? Are you sure? Are you sure you're holding it flat? Probably not. So you really want to kind of do this. That's better. Plus, you don't always want to pick up stuff in the air that you're using in lab. This is not a good idea. Oh, let me just look at this real quick. Pours it on head. So you don't need to do that. Little tips. We have some measuring pipettes. We have some that are like this. We mostly would use a burette in that situation. And then again, this volumetric pipette, they have one mark, and we have a lot of those, and I like those a lot. So we have all of this stuff, and we'll just kind of play around with it tomorrow. Your standards just say that you know how to prepare solutions, but I think it's cool to just actually make them. And so next year in AP, like you'll make all your solutions for your labs. And the reason I don't do it is because it's a very common type of AP exam question. A student needs to prepare a solution 250 milliliters of 8 molar. Well, that's high, 0.8 molar, whatever. How do you do that? And then you have to write about it. So anyway, again with the burette, we did this at the beginning of the school year. Remember, like with burettes, the numbers kind of go backwards. And so this right here is 23, and that's 23 and a half. And so this is 23.45, not 24.55. Okay. So you read these from the top down, not the bottom up. So the top is 0, and then like way down here is 50. Does that ring a bell to you? So that's a minute ago. That's a burette. And so when you want to make a solution, I do want to add to this because this is something that I think they're missing. When you make any solution, you really do want to start with a little bit of water down here. You always want to put a little deionized water in there to start with, okay? Then you're going to put your solute, and then you're going to be able to kind of mix it. While there's a lot of space, you want to mix it. Some of the things that we dissolve, they actually get quite hot. And so if you start with just your salt and then you start adding water to it, it'll be very hot, and so it'll be uncomfortable to mix, and you may risk getting injured or breaking the glassware. So I always like to start with water, and you can tell, like at this point you would already have your solute measured, and you can see if your solute is just a little bit. You could add safely a good amount of water and be okay. But you know, you're going to put the cap on it, and you're going to invert it, and I'll show you how to do all this, but you just kind of gently turn it upside down like this. And then you can put more water, and then you're going to add water to it to the line. This part's a pain in the. So when you was it your class that I showed how the salt water? It was the other class, wasn't it? Well, anyway, let me show you. I'll show you something. So when water, here's water. I have these little models. Hopefully, I'll get these next year. But water has these positive dipoles for the hydrogen, has a negative dipole for the oxygen. They stick together like this, and that's what hurts to do a belly flop, and that's why it takes forever to get spaghetti, because you have to separate them. They don't want to separate it. Those are called hydrogen bonds. They're not real bonds. They're just magnetic attractions between the molecules. And so, if this is sodium chloride, that would be sodium because it's smaller, has one less energy level, right? Plus it's an ion, that's a positive ion. So if you lose an electron, you kind of lose weight. Remember that? Anyway, so salt goes into water like this, and like the chlorine, chlorine's negative, yeah? And so what side, the hydrogen side or the oxygen side would get with that? The chlorine's negative. The hydrogen side. So look. I need some more water, I'm thirsty. Okay. And so that happens, and then the sodium ion, the negative dipole of the water, kind of gets around it. And so when you put a solute in water, and I put these back together, it really doesn't end up taking up any more space. Like you'll have a bunch of salt, and then when it mixes in the water, it gets in between the molecules, and then the solution will like go down. You'll have it to the mark, and you'll invert it, and then it'll go down. You'll get to the mark, you'll invert it, and it'll go down. You have to do like 4 or 5 times. But you're not done until your bottom of your meniscus is at that calibration point. It's okay to be under it because you can always add more water. If you go over it, can you do anything about it? No. No, you can't. So it's better to be kind of patient with it, especially after you've like painstakingly measured out everything. So anyway, that's how you do it, and then you'll put the little. We have snap caps. These have the glass kind, but and then you label it with a marker. And so if I was to tell you to make a 0.1 molar, sodium chloride or sodium nitrate solution, you would label it with your little pen, and it's just like a wax crayon, and you would put it up. So, the flame test we did? We're going to make some of those solutions. Okay, so kind of going back to some vocab. Saturated means it's holding all that it possibly can. Unsaturated means that it could possibly hold a little bit more solute. Okay, so. And then supersaturated, does anybody's parents or personally, maybe you do this, make sweet tea, but you like heat the water up first so you can get more sugar to go in there? Y'all know people that do that? Yeah, we're in Georgia. Y'all know people like that. So you're actually making a supersaturated solution because the amount of sugar you're able to dissolve in the water is it will only do that at that higher temperature. So that's a supersaturated solution. So super sugary. So anyway, unsaturated, if I put salt in this 100 milliliters of water and it all dissolves and there's none left, and I could fit some more in there, that's unsaturated. Saturated solution, if I add it, then there's it's going to hold the maximum possible, and there may even be some that doesn't dissolve. And that's how you know the tea's good, when there's like a couple little grains of sugar in the bottom. Is that right? Okay, so molarity. What molarity is, again, it's capital M. It's moles of solute per liter of solution. Remember, per means divide. And the units are capital M. And then, look, don't let this freak you out. Look, this is math. Don't be scared of math. This just means, y'all know what a -1 on a number means. It's on the other side of the fraction bar. Yeah, so that's just moles per liter. That's just that. Whatever. I'm scared. That's not scary. And so, a 0.5 molar HCl solution, that's what you say. It's 0.5 moles in 1 liter solution, or it's 1,000 milliliters. All of our glassware and all the stuff that we're going to be using tomorrow is in milliliters, and so you're going to have to make that conversion. And notice it is liters of total solution. So like if you had to make 300 milliliters of a 1 molar solution, that doesn't mean necessarily that you're going to use 300 milliliters of water. it means that you're gonna, when you add it up to the line, you need 300 milliliters total. Okay? So gotta be careful with that. Okay, so let's look at one of these. I've already kind of worked out some of these. This was the do now. Do you want me to kind of start over? Do you feel okay about this? So who was out when I explained, or you missed the pogo for how to do molarity? So everybody was here? All right, well, let's look at it then. What is the molarity of a sodium hydroxide solution? And I like to just, I'm gonna fight this out. It's kind of, this is therapeutic. It's like one of those adult coloring books, which, does anybody like those? I'm not into that. I feel like I got other stuff to do. You know, I'm over here coloring birds. No. I don't have time for that. So let me just start this from the beginning. All right, so molarity is moles per liter. Moles of solute in liters of solution. And so as I'll read these problems, and I hope if you don't learn anything else from me this semester, which is good because I'm only going to be teacher like for 4 more days. But if you didn't learn anything else from me this semester, as I'm reading a question, I'm going to be reading and labeling as I go. What is the molarity? So I'm solving for capital M, right, of a sodium hydroxide solution that contains 24 grams. And so can I do anything with grams in this? No, so I'm going to convert that to moles. Dissolved in a 300 milliliter total volume. So I need to convert that to liters. So that's my moles waiting to happen. That's a one-step conversion. And then the 300 milliliters. Does anybody get sad? Have you figured out how this works? Move the decimal 3 times? Yeah, okay. So, and I showed y'all how to do that. So the bottom of this fraction is 0.30. All these zeros are significant because that final 0 is after the decimal. So that's liters. And then that top number, I do have to convert to moles. The molar mass of sodium hydroxide is 40 grams, and I know that because it's a very common one. And so you can look at this and tell it's 6/10, right? See how that's 6 over 10? And so that's 0.6, and I have 3 sig figs. And look, I don't even need a calculator. Feeling like a nerd right now, but so that ends up being 2.00 molar sodium hydroxide. Did I like blow anybody's mind there? You should have started with this like long time ago. Would you really want to do stoichiometry right now? Shake said no. Okay. Perfect. So anyway, we solve for the molarity, and capital M is for molar. Go S. So let's go ahead and see if you can work this out with a friend. There was one little typo. This should be solute. So solute, and the solute in this case is lead nitrate. And it's not just lead nitrate. What is the lead? Lead what nitrate? Lead 2 nitrate. You know why? Because nitrate's 1 minus. And so if I have 2 of these and 1 lead, 2 plus. Reviewing the naming. What's happening? Okay? So go ahead and see if you can convert to moles and then find the molarity. Did anybody want to cut on the water molecules? What did I do? Oh. What happened? Oh, okay. You look like when you said it. Yeah. Pass it down. Anybody have any trouble? Should have done it this morning. Okay, so let's see what we got. Everybody done? I see a couple people right next to me. I'm gonna quietly kind of start looking this out up here. The molar mass of this is quite high. What'd you get for the molar mass, Allie?
331.22 grams.
Okay, and so, and that's going to be the moles. And so, to find the molarity, I'm going to take that answer, put it on top, and then the volume is 0.1500 liters. And what did you find for the liters, Noah? Oh, not liters, moles. And so, when you do the math out, you end up getting maybe like 0.8 or something, 0.9. What is it?
0.927.
And that's 0.927 molar lead to nitrate. All these parentheses. So, anyway, is that the worst thing that's happened to you today? No. So, there's that. I have to teach you one more little thing. It's super easy. All right, so sometimes, like today, in Wildcat period, me and my little lab aides, we took the 12 molar hydrochloric acid, and it's a liquid, right? If I wanted to prepare 3 molar hydrochloric acid, could I like mass out 3 grams of solid hydrochloric? That's not a thing. It's a liquid. Hydrochloric acid is actually hydrogen chloride gas in water. And so when you open the bottle, when you have that really concentrated kind, actually you can see the vapors come out. It's super creepy and scary. So anyway, you end up diluting it. And so what you do is you add water to it. And you decrease the concentration. Like if you had really concentrated Kool-Aid and you add water to it, it's going to get lighter in color and, you know, more dilute. So if we look at this, this is kind of what we did today with acid. We started out with, if I count these moles, 1, 2, 3, 4, whatever, I think it's 18. Doesn't matter. Are y'all looking? Humor me for a minute. So let me show you, like we started out with 12 molar hydrochloric acid. And so within that liquid we had a liter, it was a liter bottle, might have been a 2-liter bottle, but whatever. Let's say it was a liter bottle. In that liter bottle we had 12 moles of hydrochloric acid. And so notice here, if I cut this in half, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. It is 18. For if this is 1 liter, and then all of a sudden it's 2 liters, what's the molarity of the new solution? Talk to your neighbors. Talk to your neighbor. What would be the new molarity? I doubled the volume. This is a tough one. Batting zeros. Okay. Should just pick people. Chelsea. Chelsea, what's the new molarity? 9 molar? Okay, if I have 1 liter and I ended up with 2 liters. Oh, you know what? Let's make this. I see why you said that. So yeah, I counted 18 and then I wrote 12. I was
I got confused too.
I'm really sorry. So better. Now what would be the new molarity? Everybody okay with that? All right. So what do I get when I multiply 1 times 18? Yeah, and what do I get when I multiply 2 times 9? Do you think that's a coincidence? No, that's actually the formula. So the molarity, which is 18, times the volume, which again, in this case would be 1, equals the molarity, which would be 9, times the volume of the second one. That's what we just derived the formula. Tough. Y'all hear like random flute music?
Yeah.
Oh, they're watching something about the Galapagos. Have you ever been there? How do you know? I'm trying to eat your face off. Just kidding. It's in tortoise and they're herbivores. Just kidding, just kidding. Okay. Alright, so what we just said was, we start out with something concentrated. If we double the volume, then we would, by definition, have a diluted solution. And you can see that the number of particles gets spaced out more evenly by the water. And the water here is not drawn, but that's what's happening. Okay, so let's look at this. I want you to answer this for me. The circle labeled A represents a unit volume of a solution. Explain the changes that must be made to A to get what is shown for B for the particles of solute, and then from A to C. So basically, what would I need to do to A to get B? And then what would I need to do to A to get C? Talk to your friends. Got it? Alright, so what would I need to do from A to B, please? Rosita. That's actually a good answer.
Hi.
What else could I do to it? Evan. Thank you. Somebody this morning said to pour some out.
It works. Yeah.
If you added solvent.
Yeah, well, if I added solvent, I would be adding water. So, would that, to go from A to
Space
B,
it out. Well.
you got your,
It's up. You're taking it away. Okay.
you could. If I add more solute, then that would work. Lucy M, what would I do to get from A to C? Yeah, add more solvent.
I was thinking C. I was looking at it.
Good. Alright, so everybody okay with that? This is really difficult. No? Okay. Moving on. So here's the formula I just showed you. I will tell you something. Do you see how the volume here, does it say liters? And so tomorrow, most of our stuff, I've already said that, most of the glassware and stuff is in milliliters. And so with this formula, as long as they're the same, you can leave them in milliliters. So you can be like, 4 molar times 100 milliliters is equal to 2 molar times 200 milliliters. It can be in milliliters. You don't have to change it. Let me show you. So this is what we did today with the acid. Again, please, for the love of God, you're supposed to start with some water in there. I'm sure. Okay? Like you don't want to start with it empty. That's a bad idea. There's a rhyme and it goes like this: do what you oughta, put acid into water. That's the thing. Yeah, water. And let me tell you why. The heat of solution, when the water comes around and sort of breaks apart the acid, I shouldn't say breaks apart, it separates the acid molecules. The heat from that is so intense in some acids, strong acids like that 12 molar acid, that if you put the acid in first like this, and then you put water, it'll actually boil the water and it'll spew up into your face. There's videos on that on the internet. Yeah. I'll show you if you want.
Yes.
Yeah.
Okay. I'll show you in a second.
It's awesome.
Y'all gonna have to chill it out. I need like 5 more minutes. I love you. I know. Stop. I'm sorry I shared my water molecules with you. Alright, look. So let's make sure we understand this, okay? Again, as I read the question, I'm going to be like labeling what I'm doing here. 18.5 milliliters of a 2.3 molar hydrochloric acid solution is added to a 250 milliliters of water. What's the concentration of the solution? Do you see how I have 2 volumes and 1 molarity? Do I have anything up here about like grams or moles or anything? So that's how I know that, and you can kind of tell like I started with something and I'm ended with something else. That's how I know this is the M1V1 M2 V2. So the molarity times the volume of the first thing equals the molarity times the volume of the second one. So this one goes together. So this is my V1 and that's my M1. So those were together at the beginning. And then it says that I added it to 250 milliliters of water. That's my second volume. Now if I add 18.5 milliliters of water and then I need volume 2, is the second volume 250? Do you see what see it? So the final volume, see what I'm doing here? Am I doing a magic trick? You okay? And that's my V2, right? And then what's the concentration? So they want to know the M2. Let that soak in for a minute. Cool? So I'm solving for M2, so I can go ahead and rearrange my formula. I got to get M2 by itself, don't I? Yeah. Divide both sides by V2. And then, V2 goes away, cancels over here. By sand? Now you fill the stuff in. So M1 is 2.3 molar. V1, and again, like I said, you can leave it in milliliters because they're both in milliliters. And then V2 was 268.5 milliliters. And that equals M2. And so you just do the math. Now, let's use our heads. Praise talk. Let's just use our God-given brains, okay? So if I start with a 2.3 molar solution, y'all, and it's 18 milliliters, and I add 250 milliliters, so now it's 268 milliliters. What do you think should happen to the molarity? You're really watering this down. Do you follow? Yeah. So my second molarity should be quite small. And so anyway, now you just push the buttons on your calculator. Bang on the calculator. I hit the buttons wrong. That's funny. So I have to have 2 sig figs, so I get 0.16 molar hydrochloric acid. And that makes sense mathematically because I really watered it down, pretty much more than 10 times. Because like 10 times the volume would be 180, and I watered it or diluted it to 268. So you can see that 0.16, like 16 cents is definitely less than 10% of basically $2.30. You see how I'm doing that there? Alright, so there's that one. Alright, so last line. And so here's how to do it. A couple of the questions you're gonna have to answer in a second actually ask you how to do this. And you're gonna have to really do this tomorrow. Like I'm gonna give you a little card and it's gonna say, I need you to make such and such and such and such. And you're gonna have to do it. So if I was asked to ask you to have, if you had a 4 molar stock solution, which is kind of what you start with, my M1. Describe how to make a 1 liter solution. So that's my V2, M2. So what do I need here? So see, here's V1. So you have to do the math, which you can do the math, right? That's not a problem. But then the V1, the initial volume, you'll need to measure out 190 milliliters. So you're going to get that volumetric class, that teeny bottle looking thing. Okay, and you're going to put some water in it, right? You always want to start with a little bit of water in it. You're going to use a pipette, and you're going to put 190 aliquot, it's just what you started with. Okay, stock solution into the volumetric flask. Fill the flask with water until the meniscus is at the calibration line, and you're going to mix thoroughly, and you're going to do that by inverting it. So that's how to do. It's not the worst thing that ever happened. All right, so now you guys can sort of start on your work. Oh, I do need to tell you one thing. If you'll go ahead and look at your practice problems, look at number 8. So on number 8 and 9 and I think 10, it's really not that bad. But what we've been doing, you guys, is we've been going and solving for molarity by having moles over liters. Well, what if they ask you something like, you have a 2 molar solution, y'all watching, and you have 100 milliliters of it. That's 100 milliliters. See how I did that? And then what if they said, like, how many moles of solute is that? See what I mean? You just use formula. It's not the worst thing that ever happened. We've just been solving for the capital M. You can certainly solve for this or this. Now, what if they ask you to give you grams of solute? Can you do that mathematically? You can do that. So just heads up, sometimes, it's not such that you just put it in and plug it in. You have to sometimes solve for other parts. So go ahead and knock these out. Y'all have a while. And let me know if you need help. Everybody cares.
At most, maybe 20.
That's what I'm saying.
Like,
Thanks. This is what it looks like when you don't go to the tin bin. Got it? I don't eat Doritos. Take that, slaves.
but we love Doritos.
Wait, did you say Doritos or Doritos?
Both. Okay, well, as long as Fritos are well, all right.
Mountain Dew. Where's my Mountain Dew?
Did everybody look at my water molecules?
you have like,
She is grounded. She's freaking out.
He was trying to get Mr. McNair to approve some reference sheets that
We don't need them making a reference.
Just like teach, make them learn it without it.
well, I think he didn't want the stoichiometry one. He was trying to get like the polyatomic ions.
Yeah,
And,
she was freaking out about this.
well, there's 3 naming ones, but I think 2 of them are polyatomic.
I remember looking at the test and being like, what's that?
That would be
Me
great.
too.
I
I was so.
As we
like-
work through this week, I'm just gonna kind of review as we do stuff. There's no need in wasting time. That thing is curved heavily, and y'all are going to use stuff.
Yeah, like, today, like, this Spanish episode, somebody made a 33.
Dude, that's
Second
funny.
curve.
Nobody's using 33.
Well, because you take the square root and multiply it by 10.
Uh,
We made